Hey everybody, today we're going to be analyzing the landing legs of the lunar module. So you can see I have it up on my screen right now, but we're going to be recreating this throughout the course of the video. So this video is going to be split up into three parts. In the first part, we're going to take a look at all the documentation for the landing legs in the lunar module and get an understanding of what all the struts do and how the deployment mechanism works and how we can kind of break this down in a way that makes sense. In the second part, we're going to be looking at the 3D CAD that I did. So I'm not going to recreate the CAD live, but I will step through it like feature by feature so I can show you guys exactly what I did and how I did it. And then finally, we're going to be starting from scratch and recreating basically what you see here on screen. And we'll go through all the details and what elements I used and how I represent things in a finite element analysis model. So this is FEMAP with NASTRAN, which is a very common program in the aerospace industry. NASTRAN stands for NASA Structural Analysis, and FEMAP is like a post-processor program that runs the NASTRAN sort of analysis solver. So like I said, this is very common in the aerospace industry. It's what I have most of my experience on, and also it has an educational license. So I will put a link to that down in the description below if you want to follow along as well. So for the CAD, I'll be using Fusion 360, which is just about the best CAD program that you can get for free. Not part of a company, just as a hobbyist. So if you're looking for CAD work, definitely Fusion 360 is the best choice. If you don't want to spend any money. Okay, and then one last thing before we begin, very briefly about me. I do have a degree in aerospace and mechanical engineering, and I worked in the aerospace industry for a number of years, particularly doing analysis and using FEMAP. That's why I, kind of gravitated towards this program because I really, really like it. And it's very powerful, and they have an educational license, which is awesome. Anyways, like I said, I work professionally in the aerospace industry, so that's where I gained most of these skills and knowledge for analysis. I'm going to share that with you guys here today. But also, keep in mind, in sort of a professional environment, everything is very rigorous, and there's a lot of reviews. Like there's buddy reviews, analysis reviews, design reviews. Whereas here, I'm just kind of doing it for fun. So while I'm going to be doing all the techniques that I learned professionally, keep in mind that this is not a actual thing that's going to go to space. This is me making a kind of a teaching video for fun. So at any rate, I think let's just go ahead and hop in here. So like I said, I might reference this a few times, but we're not going to use this. This is more just for show and for me to prep. We're going to start with understanding the whole structure, right? So I found a number of resources. I will also link these in the description below. So let me just show. So this is it's like a PDF. It's like 17 pages on a bunch of, it's actually on the lunar module as a whole. But it's pretty good source for information, and a lot of the reading is very concise, and like there's a whole section on the landing gear and all of the constituent parts. So would recommend checking this out if you're interested, as well as here's a longer report on just the landing gear. And there's a number of figures that I found useful, like this one that shows how the strut deploys, and then there's a few others in here that I won't try to find, but they're in here. And it's also a good resource. So anyways, I've picked out kind of the important ones, and then I also have some real hardware pictures down here. So I always think it's super super valuable as an analyst to make sure you get as hands-on and in tune with the hardware as you possibly can. You never want to be kind of alone in an analysis bubble, because at the end of the day, your job as an analyst is to represent reality in the simplest way that you can. And to represent reality, you really need to have a good understanding of the hardware and what's going on, so that you can, create a element or set of elements to represent, something fairly complex. Okay, but let's take a look here. Let me zoom in so you guys can actually see. And I think there is a way I can make this workspace bigger. Okay, I collapsed. Okay, so I collapsed a bunch of stuff so you guys can see a bit better. So at first glance, this looks like a mass of struts, but when we break it down into its constituent parts, hopefully it becomes fairly easy to understand. So let's start up top here. Actually, will this surface right here that I just put an X through is, let's hop over to a image of the lunar module. It's this flat surface right here, that same one. So basically there's 4 landing legs all around the lunar module, and they attach to the structure on these flat surfaces. So that's kind of orienting ourselves in space here. Now we have these 4 struts outlining like that. So these are this is the outrigger structure. You can see it's labeled right here. So this essentially just forms a fixed point right here, right? This doesn't move. This point, when the gear deploys, the main strut or the primary strut here rotates around this point. So something worth noting is that to fix a point in space, you actually only need 3 struts. The 4th one is actually redundant. Like if you're setting up a camera tripod, your tripod only has 3 legs, because you can have a stable 3-leg structure like this, and as long as you do your joints right at the confluence point, then essentially you'll have a fully defined structure that's fixed in space. And tripod, like strut tripods, are fairly common from what I've seen in spacecraft. So why did they add a 4th strut? I'm not in the heads of the designers in the 60s, so I can only guess, but I would imagine they wanted a nice symmetrical structure for loading, so they didn't want to just eliminate one of these and then have all of the compression load go through that strut. That's a possibility. And then they could have just sent this guy straight to the middle, and then you do have a like nice symmetrical loading structure here. But then you have all of your load going, well, not all of it, because it's split between tension in these members and compression in this member, but you have a fair bit of your load going right into the middle of this panel. And if the lunar module structure is set up in such a way that like this corner is very stiff and this corner is very stiff, like when it's interfacing with other panels and members of the spacecraft structure, it might have been more efficient to just send 2 struts out to these corners than just straight to the middle. So it's always good to kind of look at these designs with a critical eye and try to think like, okay, why did they, if 3 struts can define a single point, why did they go with 4? So maybe off the mark there, but that's just my sort of observations. So anyways, we know we have a fixed point right here. That's what the outrigger does. It's just basically dumb structure. So this is the primary strut right here. It goes all the way down. Oops, sorry. That was a terrible line because I hit the mic stand and it caused my mouse to veer off. But this is the primary strut. So this takes, down here, it takes all of the force of landing, including some bending. So there's vertical forces here, and then there's, forces in the horizontal direction if, the lander comes in with velocity in the direction of, along the ground, or if they're on some sort of slope. So this is in bending, this section, and then also this section a bit too, because, it'll tend to bend around this point and be reacted up here. But generally it's in compression when you land, right? Compression goes up the strut like this. And then this is actually designed to be a honeycomb crushable. So essentially it's like literally a beehive structure, like honeycomb of aluminum. And there's just like a kind of an actuator face in here that pushes on it, and at a certain force that is, determinable based on like the density of the honeycomb, it'll start to crush, and that can give you constant force in the structure, and as well as like a capped acceleration so as to not overstress the lunar module as it's coming in for a landing. So we're not going to analyze the honeycomb. So I do have some experience with honeycomb, and generally the force deflection curve will look something like this. So it goes up. It hasn't started crumbling yet. It hasn't started buckling. So the force is just going up, and then at some point you reach a critical load at which like the first bit of honeycomb starts to buckle, and then you have a drop, and then you go with like constant force as the thing just buckles out. So this is like just in sort of the linear regime where there's no permanent damage in the honeycomb until like it just starts buckling, and then there is a drop in load typically associated with that. So what we're going to analyze is this kind of peak right here. So we're not going to worry about the honeycomb crushing, and even if we did want to worry about the honeycomb crushing, we would probably just do a static snapshot at some point rather than try to analyze the travel of the honeycomb. So there's that. There is also honeycomb in these 2 struts. So if there's a significant amount of horizontal velocity that needs to be attenuated, then essentially these struts also can crush. So that's the primary strut and the secondary strut both have honeycomb crushables to attenuate the impact on the lunar surface. Okay, so I touched briefly on the secondary struts, but essentially, you have a point up here, and imagine this kind of like as a pendulum, the primary strut, and it can swing like in any direction around this point. And what arrests that swinging is the secondary struts, right? So imagine you have a pendulum, comes down, and it can swing in any which direction that it wants to. It can swing, in a circle. It can swing back and forth, left and right. So you need to constrain that swinging motion. So that's why you have 2 struts. Now, let's just imagine you put just one secondary strut on. right? So now you've constrained one of the swinging directions, but these are both, pin type rod end joints or ball joints. So if we draw a line between those two joints, this whole thing now, this guy and this guy as a triangle, can now swing around that axis, right? So we have a secondary strut, or I guess tertiary strut, to constrain that swinging. So essentially this creates, another, like assuming this is a fixed point in space, which we'll get to in a second. This is a fixed point in space. This creates another fixed structure. Okay, so now hopefully that makes sense. We got the outrigger, we got the primary strut, we got the two secondary struts, which constrain the primary strut. The deployment mechanism here. This is a little bit more complicated. So first things first, let's scroll down and look at what it looks like when it is stowed. So we've been looking at the deployed position where we have the primary strut here. This right here is our secondary strut, and then outrigger is right here. And obviously you can see the primary strut rotates around this position to go into the stowed position during launch. Or I guess nominally during launch, it's in the stowed position, and then after launch, it deploys itself permanently. So we can see we have this triangle right here, right? And if we jump up here, that's that same triangle, so that all makes sense. And then it rotates around this point, so the triangle like literally unlatches itself. Like this is that same triangle that has rotated forward like that. Okay, so how does that happen? I won't go spend too long on this since it's not super critical to the structural analysis that we're going to perform here, but I think it's still interesting to understand. Okay, so we have this very helpful diagram for understanding how exactly this thing deploys. So this is the point that I was just showing, that it rotates around, and then if this were to extend out, it would connect. So this strut and this strut are essentially this strut and this strut. It's like that's that same triangle, except they just cut it off, so the figure isn't massive. And that's the same thing over here, just for your information. So these are from the same perspective with the lunar module surface right here. Okay, so how exactly does this thing work? So you can see right here, there's an up-lock chuck holding onto the triangular bit right here. When ready, I think they're in lunar orbit. I can't remember exactly at what phase of the mission, but definitely when the lunar module has deployed from Saturn V, there's like an explosive charge in here, which is used fairly commonly in the aerospace industry, even still today, like explosive charges that sever nuts or bolts or connections, or even like cut bridles or ropes are still fairly common. So essentially, this is held until when they're in space and they can sever this. And this whole mechanism is held in tension throughout launch. So essentially, once that connection is severed, the deployment is automatic, and it just uses like energy held in the mechanism. Before launch, when they install it, they preload the whole mechanism to get it in the stowed position. So how does this all work? It's actually not too complicated. So this guy right here is a spring that wraps around this crank. So this is like a coiled up spring. So when the chuck over here is severed, which is holding this guy and holding the spring in tension, essentially this crank starts to rotate around this point, which is going to drag this guy up, which is going to by turn drag this guy, and this rotates around this point. So essentially, when we sever that connection, we have a moment created by this crank assembly, this crank and link, to rotate this entire structure around this point. So then this point, which is like the upper half of that triangle that we've been pointing out, will rotate up and around and into here. And then real quick, how does it lock? So essentially, this is, I managed to find a hardware picture. This is pretty cool. I always love seeing like kind of the old hardware. Like you see all of these, like, you know, big kind of assembled stuff, but you rarely get just like a super close-up view of like, here's a singular component. But anyways, here is that lower connection. This is the point that it rotates around. You can see right here. You can even see the jaw here, or the clevis is also right there. And then here is the upper strut, right? And you can see it has a big old hole in here, and it has this roller, this circular roller right here. Let me zoom in just in case. Whoops. So you can see it has this hole and then a circular roller. And while we're on this picture, you can see we got some tubes. This is just like probably, I'm assuming this whole thing's aluminum. That's probably a safe bet for just about any aerospace metal is going to be aluminum. Might be titanium if they're really trying to shave weight. But I would imagine this is just aluminum. So you can see we have a tube here. This will be a hollow tube. These are rivets. And then over here, they actually have a welded connection. This is a machine part, right? And then this is another tube, machine part, rivets, probably welded on somewhere in here, but they might have just ground or sanded down the welds so that you can't see it, but they left it over here. So this could be a really fun part to do a separate analysis on, because we have like a very detailed sort of picture of it, and this could be kind of fun because you could do like a solid mesh here and like a plate mesh here, or even a you know, a beam. So I always think it's, you know, fun to look at the old hardware pictures as well and go through those. Anyways, hopefully I'm not being too long-winded here, but essentially my point before we digressed was that there is a roller and a big hole here, and you can see there's this claw looking piece, and this is the roller right here, and now the claw piece has gone through the roller, and the way that works is it's actually linked to this same crank. You can see there's this surface right here, and then it drops. This whole big arm rides along the crank, and it has a spring to keep it preloaded. So as this guy starts to rotate, it eventually reaches a point where this surface that's contacting it is past this point, and this whole thing will you know, relieve itself of its preload, and it will snap down. So that's what this downlock spring does, and you can see now that's that same drop point right here, and the this whole claw mechanism has snapped itself shut, and now it's permanently stuck, right? You can't open this thing unless you got some technicians out to the moon to open it, but you know, they don't need to open it because it just sits on the moon. So that's how this thing is like permanently locked. Essentially, this claw comes down and locks into that gap in the roller, and just locks the whole mechanism together. Okay, so that is how this thing works. So now we can see, we know that this is, zoom in a bit closer, we know that this is the roller, and it has a claw that snaps in there. So essentially, point right here is fixed, this is down here, and it rotates up. So we can actually abstract most of this away. As you can see in the analysis model, I really don't have all those linkages there. In a more detailed model, I certainly would model at least linkages in the primary load path. But this model would be used for something like a stiffness representation of the landing gear for like a full assembly, for a detailed model of like writing structural stresses and structural margins to failure. The model would be significantly more complex, and it would sort of, be, this is only 77 elements. It would probably be at least 10,000, probably quite a few more, depending on what type of elements you're going to use. So I kind of abstracted away a lot of this stuff as a stiffness model. Maybe in the future, I don't think it would make sense to do that full analysis model live for a video, but I could do it like kind of before the video, and then just step through. Maybe that would be something that's interesting. So anyways, sorry, this part's a bit long-winded. There's only one last thing we need to look at, and that is these two crossover trusses. So I couldn't find a ton of great pictures of these, because once they're on the lander, they're covered in foil. You can see here, I set this as my desktop background for the video. Everything here is covered in foil, so it's kind of hard to tell what's exactly going on. But it seems like it's illustrated in this photo that the beams are not connected. It seems like it's showing them going straight through each other, like there's a clearance hole in the sky, and this beam can pass through. So that's the way I assumed it. If that's not true, if I found other information, it would probably take me maybe 10 seconds to merge these points and analyze it as if they're connected. But just letting you know, based on this picture, I just assume that they weren't connected. And again, that's something like, that's a reason you need to be in tune with the hardware as an analyst, because, are these connected? Are these not connected? I don't know. We need to inspect the hardware and see what the constraints are between these two. So anyways, this, let me jump down to this view down here. You can see, where is it? I want a top view here. So you can see this strut will be pushing force along this direction. And that is going to want to, if this is mounted here, that's going to want to create a pretty huge moment around this strut, right? So essentially we need a brace to keep this guy from just like bending over. And that's what the cross struts are doing. So again, just looking at it from another view, just looking at it from another view here, this strut is trying very hard to bend over this guy, and this cross strut is not allowing that on both sides. And then something else that's cool is that you can see, you have this like fork piece right here, like that. So you have one mount point there, and then you have one mount point here, and like this strut goes through that point to try to like minimize the bending. And you can see we have this exact same fork part in the hardware picture that I have. So here's like where it connects to the secondary strut, and here's where it connects to the cross brace and goes through that. So again, always really cool to see the actual hardware pictures. So yeah, that does that on both sides, and essentially it keeps the the whole deployment mechanism here from bending over when a load is applied, and that also I just mentioned bending this direction, but there also is a case where you have a large horizontal velocity in this direction causing tension in this strut, and then this whole thing would be pulled in this direction. So keep that in mind. So these two brace each side, and that's pretty much all the struts, guys. We got them all. Like I said, we're gonna abstract all of this stuff out in the analysis. This strut is essentially what's responsible for keeping this assembly as one assembly and not like a floppy bit. And under structural load, it probably does very little. So I didn't include it, but again, that's another thing that, it wouldn't be hard to add, and you'd probably want it in a full structural model just to make sure it's not picking up any extra load that it doesn't, or even if it's not, critical to the structure, once it's deployed, you still want to make sure it's not going to like break and cause problems. Okay, so I think we got everything here. Hopefully that all makes sense. But feel free, we can have conversations in the comments if anything doesn't make sense, or if I didn't explain something well, I can try to make a second video or something. Let me know. Hopefully everyone's still awake. What was that? It's been 30 minutes, and we're just getting into phase 2. So I think I'll go phase 2, or part 2 will only take about I think 5 minutes maybe. I don't want to spend too much on CAD here. But anyways, so this is Fusion 360. Like I said, it is free for hobbyists, and it's pretty much the best thing that you can get without paying. So we're going to, I use this diagram, which just has a bunch of dimensions, to like try to, establish some real dimensions. I will say, they don't have, maybe they do have it somewhere, but I didn't find it in my checks, but they don't have every single dimension and feature documented. I found a lot of diagrams like this, which is kind of like general sort of measurements, but I essentially use this to like, okay, I have a bunch of measurements here, and I can kind of like do some comparisons of like size to like essentially assume or guess all the other dimensions. And again, this is something that when you're just doing analysis for fun, you can just kind of make some assumptions and make what looks right. But obviously in a professional environment, you want to have like all the proper dimensions. So this helps a lot. 5 foot, 8.86 inches. There are a few other ones that I use, like 13 feet, 10 inches. There was one that actually surprised me that they included it. Oh, right here. They included the distance from the top surface here, this guy, to the outrigger fixed point. And I was like, oh, wow, that's actually surprisingly helpful. Thank you for that. So this is essentially what I use to put together this CAD model. So I just created a flat plane here, or a surface. This isn't used in the analysis at all. This is literally just for visualization purposes. But I did, kind of use this surface as measurements for the sketch. Okay, so this is the first sketch. So Fusion does allow 3D sketching, but it's not like some other programs where you specify, I want a 3D sketch. It's all just sketch. So if you hop into your preferences, and then you just have to make sure, if you go under general and then design, you have to make sure allow 3D sketching of lines and splines. Make sure that's checked. And then when you actually edit the sketch here, edit sketch, you have to make sure 3D sketch is checked, and then you can just 3D sketch. So I tend to use a lot of construction lines in Fusion. Just press X to switch between construction and non-construction, and that helps kind of block things out. So you can see all these lines here essentially are just like getting out to the point of like, this is straight from that drawing with the outrigger point. And then a lot of these are kind of assumed dimensions, like this 40 and things like that are kind of based off what I thought looks right and what I could use as like a kind of like a ratio of dimensions on that drawing. So anyways, this is our outrigger, right? So just essentially the blue lines are the real geometry. This is our 4 points. The next sketch, I created the secondary struts and the primary strut. So again, like if you're familiar with CAD, this shouldn't come as like a big shock to you. And just doing a 3D sketch, you know, constrained it up here based on the previous sketch. Went down here based on like the length of the landing gear. I kind of guessed what looked right on the point of the secondary strut attachment, and then also, you know, made some guesstimates on where the secondary strut interfaces with the deployment truss. So again, nothing terribly complex there. This guy is, I think, just a plane. Yeah, I used that just for reference, or sorry, for the mirror. And then this gets half of all of the deployment struts. So actually, fairly important note here. You'll note that I did not just make one big line from the top point to the bottom point. This is 2 separate lines. There's a construction line under that is one big line, so I could place the 2 lines on it, but the actual blue geometry is 2 separate lines. There we go. You can see it's highlighted now. So that's very important because we need to essentially ensure that there are nodes on all the struts that come into a singular point. And that'll make sense in a few minutes. So same thing over here. So here's the triangle. Triangle struts. You can see I abstracted away essentially all the extra stuff here. If we were doing a very detailed analysis model, we could include those. But then here we have the fork. So you can see it forks right here and then attaches to this cross brace assembly right there. And again, I have reference lines to make sure it's all constrained. And then the strut interfaces after the fork. And if we jump back over the hardware position, you can see that is, you know, how it is on the real strut. You have here, 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 and here, and then here. So the top strut of the triangle comes in after the fork, right? Okay. So that is pretty much the deployment mechanism. And then I made these tubes like 100% just for representational purposes. These tubes are not used in the analysis. This is just to kind of look at all of our struts and be like, okay, everything looks right. You know, obviously this is not correct, but it's just for representational purposes, and everything looks as it should. You know, we can look at like the top view here. You can see the shape it makes, and then if we compare that to the top view of like the shape it makes here, you're like, okay, this looks right. You know, everything is where it should be, right? And I also modeled the foot pad just for flair. So this isn't used for the analysis at all, though. So, oops, wrong one. Then after that, I created all of the surface bodies. Now, this is a limitation of Fusion. Normally, I would not do this. I would just take this and like as it is, and I would export this to FEMAP, right? I researched a fair amount, and I couldn't find a way to export curves from Fusion 360. So essentially what I'm doing is cheating I literally just did a bunch of surface extrude features. So if I edit this guy, you can see like it's literally like I clicked on the line and then extruded a surface. And then surfaces are geometry that you can export from Fusion 360, but not curves. So this the surface now has a curve right on the front edge that I extruded from. So like we just use that front edge in the analysis, and you'll see what I mean if that doesn't make a ton of sense. So this step to make all these little 1-inch surfaces is just because I'm using Fusion. If I was using a different program like NX, the CAD program that's made by Siemens, or if I'm using SolidWorks even, you can export curves, but unfortunately in Fusion you can't. Okay, so then I just did like a file export, and I used, I don't know, defaulted to that. I used step. I already did that though, so let's hop over to FEMAP and okay, so now we're in FEMAP here, and the first thing I always like to do is go to view background and just change it to solid, and then go to white. This NVIDIA seems to think that FEMAP is a game, which maybe it is. So anyways, as I was saying, generally I always just go to white because for reports or slide decks, design reviews, whatever, you'll typically be taking screenshots and images. And if the background is white on the report and the background is right here, it looks, like a very professional, like clean look when you don't have like a gradient blue border around all of your pictures. So I always just do that to start with, and we'll also tweak some other view settings as we go. But essentially we're going to go file import geometry. Well, actually, is it? Yeah, file import geometry. Just wanted to make sure. And then there's landing module legs, or lunar module landing legs, that I already had exported, which is the exact same file as before. So this is it imported. Now we're going to go over to our layers. Layers are essentially how you can organize things. So you can put all of your elements in geometry in different buckets. So if you have an extremely complex model, which we don't have here, you can have like your primary, like, if you're working with a spacecraft, you have like all your main structural panels in one layer, and then you have like your brackets in another layer, you have all of your interior hardware, your exterior hardware in different layers. So it essentially allows you to see through the model and change what's currently being displayed. Let me just make sure I'm recording, which I am. Okay. So we're going to go new layer, and we're going to create a layer called main struts. And again, this isn't super necessary. I'm just doing it to kind of show you, like gold standard, I guess. We're going to call this outriggers, and we're going to call a new one, call this deployment struts, and I think that's enough layers just as kind of a demonstration, and then we can turn those on and off. And then default layer, we're going to rename this. Okay, so now if we turn off like our geometry layer, all of our geometry disappears because that's what layer we had active when we imported it. So essentially, whatever layer we have active is where, when we add elements or whatever, that's where that piece is going to go essentially. So just activate it by double clicking on it. This isn't really going to be a FEMAP tutorial per se. This is more just going to be like a kind of like a fun thing to do in FEMAP, and you can follow along if you want to. But I'm not going to be necessarily explaining every nitty-gritty detail about FEMAP. But I will say real quick about FEMAP is that it is extremely powerful because it allows direct manipulation of every single thing in your finite element model. So if you've used programs like SolidWorks Simulation or ANSYS or whatever, they're decent, but they don't really allow you to like just move a node or change an element or something. It's just kind of like all linked into the mesh of your part. FEMAP is not like that. You can literally grab a node and you can move it 10 inches away and make it like a really skewed, ugly element if you want. I'll use direct manipulation of elements and nodes throughout the course of this video to set up all my constraints and whatnot, and you'll kind of see that happening. So anyways, let's start with the outriggers, but before we can jump into meshing, we need to create our materials and properties. So essentially a material is just like the material properties. So we're going to call this aluminum. And I generally, for like rigorous aerospace analysis, you would specify, not, so like there are, if we're going to call this 2024, obviously there are different alloys of aluminum that have different strengths, but also to go like a level deeper, even like the way you form the same type of alloy can give you like slightly different strength property. So like an aluminum plate that is greater than 6 inches will have a different property or like different strength values than an aluminum plate that is less than 6 inches of the same alloy. If it's in the form of tubing, it'll have different strengths. So generally you want to like be very clear, like plate 1 to 3 inches or something like that. I'm not going to do that here because I don't have all the data on my fingertips and it doesn't add much to analysis, just for fun, because generally the differences in strength are pretty minimal, and I'm not even really putting strength values in here. It's more differences in stiffness, which again are not super huge. So Young's modulus, 10,000 KSI. So I'm going to 10, 1, 2, 3 for 1,000, and then 1, 2, 3 for KSI. So FEMAP has no units. You just have to make sure everything you input is consistent, and like all the math will work out. So I'm going to be using pounds and inches. Sorry for the metric people. Maybe I'll kind of do 50-50 on this channel, metric, non-metric. But this was NASA in the 60s. So all of this stuff was certainly in pounds and inches. And then Poisson's ratio, I can't remember off the top of my head. I think it's 0.33. But again, I would look at the MMPDS data book, which is like the kind of like official aerospace data book for metals that conform to specs, to get all this data. But for now, all we really need is Young's modulus and Poisson's ratio, and mass density. You definitely want that if you're going to be running accelerations, but we're just going to do forces, so we don't need that. And then limit stresses, I almost never use these. You can have FEMAP output comparisons to the limit stresses, but generally I've found that I like to just do it myself, and pull stresses and then write my own margins. So all I really need for like a basic structural analysis is Young's modulus and Poisson's ratio and mass density if I'm going to be doing acceleration. So might as well just put it in 0.1, just so we can have it. Okay, so now we got our material, and then property is essentially an application of that material. So if I click on, I'm going to add the material aluminum 2024, and then these are all the type of elements that are in FEMAP. So what we're going to be using here is beam, and then we're also going to use spring/damper. These are one-dimensional elements. In the future, I will certainly be doing two-dimensional like plate elements on this, which is like, essentially you compose your part made of squares and triangles. Laminate is another big one that I use for analyzing like composites, like carbon fiber. And then solid is literally like if you've done like basic analysis, where you just hit mesh on a part. Solid elements is what that uses. It's like tetrahedrals. And then there's mass elements, rigid elements. I use rigid elements quite a bit. I don't think we're going to use them here today, but in the future we certainly will. But anyways, we just want to make a beam. Okay, so title, we're going to call this AL tube. And then we're going to do 3.0 by 0.08. So 3.0 is the diameter, 0.08 is the thickness. And then we're going to go hit the shape button. And this essentially allows you to select a shape, circular bar, oops, I want circular tube. And then radius 1.5 for a diameter of 3.0, and then thickness of 0.08. So a pretty hefty tube here. And there we go. And now hit OK, and that creates a property. So essentially you have your material, which is just like your properties for the material, and then is your material like Young's modulus, Poisson's ratio, and then properties are essentially applications of that material in the form of elements. So let's go ahead and start meshing the outriggers. So I'm going to hop over to the meshing toolbox. I'm going to go to mesh sizing and then increase. And then we have to make sure I'm doing the right one. So let's start with these. So beams are exact elements. The accuracy of a beam is not dependent on the amount of elements that you use by any means. However, if you are doing analysis like buckling or modal, the more elements that you have, the more modes that your finite element model can pick up. Because essentially, if you only have one element, you can't get like a sinusoidal wave by any means because you only have one element. So I'm going to go for most of these, like these long struts, I'll probably go with 4. So essentially I'm doing mesh sizing. I'm going to increase to 1, 2, 3, 4. And I'll do the exact same thing on the other side. Now this top one, I'm actually only going to go with 1. So I'm going to go set to 1. And you'll see why we're going to make a tapered element for that. So you can see, if you hop over to the hardware pick, you can see this beam is actually tapered. So we're going to represent that. So I'm only going to do one element. You can certainly do a taper with multiple elements, and it's quite easy actually. It just takes more time, and you need a bunch more properties to make sure you represent the full taper. So just for ease of my life doing this video, I'm only going to do one element for the taper, but you can certainly do 4. Okay, so now we're going to go to mesh, geometry, and curve. So let me make sure, I think we're in the outriggers. Let me just make sure. I always put stuff in the wrong layer, and then I have to move it later. So I'll probably do that in this video at some point. Mesh, geometry, curve. So rule of thumb when you're meshing, says select curves to mesh. Whatever you select in this dialog box, it will assume that you want all of the coincident points to be sharing the same node, so like they're essentially all connected. So I'm going to select these 3. There might be some joints going on in there. I couldn't find any great hardware pictures, but that being said, we're going to abstract that away for now and just assume that this is all 4 of these struts are fixed together. And again, that's something that we could, do more granularity on in a larger, more detailed model. So we're going to hit OK. Brings up a second dialog box. This asks me what I want to generate: elements and nodes, coordinate system, element and node IDs, and then what property do we want to use? So this is the one we just created, so we want that one, and hit OK. Element orientation. This is quite important if you are using elements that don't have the same geometry in all directions. So like an I-beam or even like a rectangular tube. Those, you can orient them differently. For circular tubes, it doesn't really matter. So I'm just going to put our vector as 0, 0, 0, 0, 1, 0. And now that's generated and you can't see it yet because they are beam elements. So if I oh, I got really confused there. I was like, where are they? But I forgot to change the property color. Let me turn on thickness cross section. So there we go. So this is how you represent beams in a way that makes sense to you and I. This is just for the viewer. They are just line elements. They're one-dimensional. Let me go to our properties, edit. The color is blue. That's what we want. And then we're going to go to color with property colors. Now you can see there are blue lines. So this is essentially what the model sees, the analysis program, but just for you and I, we can see the actual geometry. So you can see here is our 3-inch tube with 0.8-inch wall thickness. Now, FEMAP also defaults to these disgusting contrasting colors. So like our elements are lime green, which I don't like. So if I hit F6 to get this, but also you can just go to view options. And then you want to go to tools and view style, filled edges. And then this is set to contrasting colors. If you just change this to black and then do use view color, hit OK. Now it's like, okay, that looks like a real thing and not like a blue and lime green elements. Okay, so there we go, guys. We have our outrigger represented with one-dimensional beam elements. So let's keep going. Let's jump into our main strut now. We're going to put our geometry layer back on. So now we need to make sure that we grab the right point here. Or sorry, the right line. There are 2 lines. We just have to get the one that's going to the same point. So we're going to go to model. And then, oh, sorry, we're not going to go to model. We're going to go to meshing. And then we're going to go increase. And then, if you'll remember, these are 2 separate lines. So I'm going to hit this guy and mesh this. So now we have 2 elements, 3 elements, 4 elements. I think that should probably be okay. Is that what I went with in the other model? 1, 2, 3, 4. Yep. Okay. So that's good. And then we want to do the same thing down here. I don't think we need 4 for that. I think probably just 2 is going to be okay. We can do 3 though. And then just so it maintains the same element size, we'll do 5. Okay, so now we want to go to mesh, make sure we're right in the layer. We are mesh, geometry, curve, and then select that curve and that curve, hit OK. And OK again, and change our vector to the Y one, and there we go. So essentially, by having a curve split here, we've essentially ensured that there will be a node here for connection to these 2. Okay, let's mesh. Let's just keep meshing here. let's go to the meshing toolbox. We're going to go to increase. Again, we want 4 nodes here. 1, 2, 3, 4. 2, 3, 4. Okay. And then we're going to go to mesh, geometry, curve. And now we don't want these two to be connected, right? So we're going to have to do them in separate meshes. Okay. Like to keep it consistent. There we go. There's one strut, and then again, mesh, geometry, curve. This guy. Okay. There we go. Okay, so now we can kind of display what the layers do. So if I turn off the geometry layer, that's gone. If I turn off the main struts layer, those are gone. If I turn off the outriggers layer, those are gone. So essentially it allows you to show some elements, but not others. Okay. So let us keep going here. We have to make sure, I'm only going to do half of these and then mirror the mesh. So we just have to make sure we get the right sort of lines here. And you'll notice that we're not using the surfaces at all. They're literally just so I can have these lines in FEMAP. But anyways, we're going to go to mesh. And then I think this guy only really needs one element. I think same with this guy. This one can do 2 just because so we can get a little bit more bending data of this arm here. This guy will do 4, the up beam, I guess you could call it. And then make sure we're selecting the right one here. We'll do 4 on this guy as well. Maybe 3 actually. I don't think we need all that granularity when we have it up here. I'm curious if I want to end up with the same number of elements. I don't think I am because I've already changed it up there. And then this guy, I think we'll probably go ahead and do 5 maybe because I want to get, it's quite long. Okay. And then make sure that was actually the right point, which I think it was. Okay, great. So now we have to think about what we want connected. So we're going to go to mesh, geometry. Oh, and by the way, I will be changing property cards on these elements. I just like to get the mesh done and then think about properties later. So this whole thing is one big strut with like the triangle and the fork. So this guy, we want this guy, and this guy. And actually, if you press this little highlight button right here, it'll actually highlight for you in yellow what you've selected. So you can see that is our strut that we want. We're going to hit OK. OK again, because it has our property selected, and then change our vector, and there we go. So that's another strut. And just to check, there's like a confluence here of 3 elements. So if we go to our selection filter, change it to element, edit 37 and 35 are the 2 nodes this is using. 37 and 40, so 37 is the common node, and then 37 and 44. So you can see all 3 of these elements right here share the same node, which is what we want, which means that they're connected. Okay, last strut, or sorry, 2 more struts that we need to mesh. So we're going to go to mesh, geometry, curve, do this guy. And then, you know what I just realized? We are putting every single one of these struts in the wrong layer. I told you I was going to do it at some point. Let me change it to deployment struts, and then I'll go to, I'll just keep meshing while we're here. Geometry, curve, this guy, okay. 0, 1, and then finally mesh, geometry, curve, okay, 0, 1. Okay, we're gonna mirror that once we're done with all of our other model prep, so that'll get there eventually, but for now, we don't have to worry about it. So I messed up the layers. So outriggers, if we hide that, main struts, if we hide that, it hides this stuff as well. So let's turn off the others and just turn on main struts. And we want to bring this guy. So we're going to go to modify, layer, and then mesh. And then we just select all of these elements that we accidentally put in the wrong place. Hit OK. And then we're going to select layer, deployment struts. Okay. And then it disappears because it moved on to a layer that we have hidden. So that's how you move stuff between layers when you inevitably mess up. Okay, so we're done with meshing of the beams, which is good. So now we can move on to connecting them all together. So let's set up our outriggers first. So the outriggers are generally quite easy. So what I like to do is use, so there is a feature built into NASTRAN and FEMAP that allows you to do beam releases. And that can be quite handy. So you can essentially say like, hey, this node or like this end of the beam, this is a connection for like a ball end, and you should release the constraint or like the hard connection between these two elements in like the rotations. But I much prefer to use spring damper elements for a few reasons. So we're going to call this a ball joint connector. So first of all, you can represent joint stiffness. This is a whole thing, like wing of analysis is like representing joint stiffnesses. Pretty much everyone that I know when I worked in industry represented their fasteners using spring dampers and FEMAP, and use there's like, you know, templates to understand the joint stiffness. I'm just going to, you know, if you had a real bolt in a ball joint, it has a certain stiffness that you can calculate. I am just going to abstract that away for now and call it 1 times 10 to the 7th, which is like an approximation of like what it generally is. So DOF, degrees of freedom, 1, 2, and 3 are translations. So essentially it's a ball joint. At that point, it's like fully fixed in translation. And then generally I like to set 5 and 6 to like a small value. That's just kind of my habit. I generally find if it like, well, first of all, like ball joints and rod ends have friction in real life. So like it's never going to be actually 0. Like it always takes some sort of torque to rotate it, especially at very high loads. In reality, this is probably like 100 or 1,000 or something like that. But I generally like to set it to something non-zero. So anyways, DOF 4, you generally want to set this to a high number. Otherwise, the strut will be rotating around itself, which is not physical, right? But we just want to make sure that like everything's constrained. So like 4 is essentially the axis of the spring, and we don't want the spring rotating around itself. We just want like that swinging motion. In reality, if like a lot of people represent struts with this, it's not 100% physical, but it, you know, to get like struts do rotate around their own axis, but like it just generally doesn't matter. But you know, FEMAP can sometimes have issues with that because it sees it as like an unconstrained direction. So anyways, I'm just going to rigidize the axis around its own rotation, and it really won't affect the analysis. So at any rate, we just created that spring damper, and now let's start with the outrigger. Let's fix it to the ground. So we're going to create nodes for all of our spring dampers. So essentially what we want to do is represent a bolted joint or a pin joint, whatever. So we're going to go to create a node, and you'll see that this is like a power that a lot of other analysis programs don't have, or it's like hidden behind other features. So we're going to go model node, and then methods, where is it? On node. And now you'll see why in a second, but we're literally just going to create a bunch of nodes on the endpoints of this node. So now you can see down here, it says node 57 to 60 created. So now we're going to go to modify, move by node 57 to 60, hit more, and then you can hit the highlight so you can see it's now highlighted in yellow. Okay, and then we're going to go move along vector, methods, locate / length, and then we're going to make our vector in the negative x direction with a length of 0.5. And now you can see that's essentially moved back all of our nodes. Okay, now we're going to go to model element. Property is going to be ball joint connector, and this is like kind of a feature in FEMAP. Your most recently made property, when you hit model element, it defaults to that property type. So like it automatically selected spring / damper. But just so you know, if you don't want a spring damper, then essentially you can just hit type and change whatever element you want. So now we're going to connect these two nodes, and that's going to create our spring damper element. We'll change the color in a second. Let me just finish creating all these. Oops, selected the same node there. 9 and 60. I'm just left clicking on the nodes here to select them. Okay, so now we've created 4 spring dampers, and I'm going to edit the property and change this to, I generally like to make my springs pink, so they're they stand out, and you can see them quite easily. So there are our springs, and I'm going to do that as well for the deployment struts. Make sure this layer is active. Turn off main struts. So these 3 points should be fixed. So we're going to go to model node. Select this guy, and this guy. I'm just hitting enter. And then we want to go to modify, move by node, 4, 5, and 10. It looks like it created for some reason. And okay, move along vector. And again, we just want to do the exact same thing. And then 0.5. Okay, great. And then model element. Like this. There we go. And finally, this guy. Okay, so now we've created a bunch of springs. These are essentially our joints to the lunar module. Like these are all of our bolted connections. So those will be fixed to ground with our constraint. We'll essentially fix this node to ground. I'll do that at the end when I have the rest of these elements. There's still some other model prep we need to do. Okay, so let's hop back over to the main strut here, and also let's turn on the outrigger. So we need to connect, we need to connect the main strut to the outrigger here. So essentially we want to create a spring, but we don't want our spring to have 0 length, because then NASTRAN is going to get extremely confused because it doesn't know what directions the spring has, because generally direction 1 is along the length of the spring, and so is direction 4, and then directions 2 and 3 are based on the vector direction of the spring. So if you make a spring that has 0 length and just connects these 2 points, then it's not going to know what any direction is. So what we want to do is we want to move the node for this guy, either 15 or 16, in the direction of the strut. So essentially what we're going to do is we're going to go to Tools, Measure Distance Between Nodes, and then select those 2 nodes and hit OK. And that is going to output us the delta X, Y, and Z of this strut. And then we want to go to Modify, Move by Node, and then, we want to select 2 is not one of the ones we saw there. So let's select again, 15 is, delete that, 2, hit OK. Now move along vector, and essentially we're just going to input those numbers. And I'm just going to go to 3 decimal places because we really don't need any more accuracy than that. Even if this was a real model, like you don't need accuracy to the thousandths for everything. Unless your component is either that small or has that tight of tolerances that it actually needs that for the analysis. But like I've never encountered something like that in my analysis days. And then length, we're just going to do 0.5. And now you can see that it has retreated this node away from the joint. And now we can pretty easily do element and just do one of these guys like that. So now that's all connected up. Okay, so now we want to do the same thing here. So we're going to go to Tools, Measure Distance Between Nodes. And I might go ahead and cut this because it's going to be quite a bit of repetitive work. So I'll just do one more kind of live with you guys so you can see it. But then we'll from there, I'll just kind of do them all offline. So we're going to go to, I have the vector. It happens to be very close to a real number, which is interesting. Move by node, and I don't actually know which node is which. So I'm going to do edit. This is 28 and 29. Modify, move by node. That's 20. That's not one. 29 is one. We're going to delete this guy. And we're going to hit OK. And then we have -15, -22, and 6, and our length will be 0.5. And now you can see anything happen because it's hidden behind there. But if we turn off thickness here, you can see that it's properly gone back. And then we can connect these up. We do want to make sure we don't select this guy. So actually, while we're here, we can do modify, let's edit 30 and 31. We're going to go modify, move by node. Delete this guy. So now we have 30. Move along vector. And then this guy should be the same except it's reversed in Y. So 22 instead of -22. And then 6 and 0.5. And there we go. It is. And now we can do model element. That guy. That guy. There we go. That's all connected up. How many more do we have to do? Maybe it's not worth actually doing it offline. We have 1, 2, 3 more to do. Might as well just do it real quick offline. Okay, we're back, and I made a mistake here, and I don't know how I made this mistake. I thought I selected these separately, but maybe I messed something up. But essentially, these elements, you can see 44 and 45, they're sharing a node, and this also has 45 in it. So I somehow, these two got melded together. That didn't happen for the rest of them, and I thought I did this guy separate, so I'm a little bit confused, but maybe I just messed up. But anyways, maybe that's a blessing in disguise, because it's a good teaching moment. It's very easy to fix this issue. You just go to model node, and with methods unknown selected, you just click on that node, and now we have two coincident nodes. And this says node 24 created, and we're gonna go edit. Oops, sorry. Oh yeah, no, that's right. Edit, and then we know this is 45, which is in both of them. We just want to change this to 24. So we've essentially created a new node and then change one of the elements to reference that new node at that location. And now if I go to modify move by node, I'm going to select 24, hit OK, move along vector, and then I already have the vector here. So it's -5.767, 13.26, and 2.11. And our length is 0.5. And now you can see there are two separate elements. And we're going to go to model element. And there we go. Okay. So I'm not actually sure why that happened, but at least that worked out, because it was a kind of a good teaching moment. We have our three connections here that you can see. We have two over here, one up here, which connects to the outriggers, and I think that's all we need. The only thing left to do is to go ahead and mirror this guy. So let me hop over to Fusion real quick. If we do, because this is the origin right here, and if we do inspect, measure this distance to this distance, it is 30 inches. I don't know if you can read that down there. Oh, it says right here too, 30 inches. And I think I might have said it on screen. Said it in a bunch of places. So we essentially want to mirror this around that 30-inch plane. So we're going to go to mesh and then reflect element, select everything here, hit the little highlight icon, make sure it's all selected, hit OK. And then these are some options that you can select. I generally don't need to change any of these numbering. You can keep it default. You want same properties, you don't want to duplicate. You don't need to duplicate geometry, and then single/multiple copies, and you don't need to repeat it at all. And should be good. And now we want to select our reflection plane. So essentially we just need to set up a base and 2 points, 3 points to define a plane. So I always set as simple points as I possibly can. So we know we want the plane to be on a y direction of 30. So all three of these are going to be 30. And then the base we'll just leave at 0, 0, 0. And we want one of these points to be I feel like the representation isn't quite right, but it should work. Yeah, I don't know what was going on with that representation. And now you can see what I was saying here. If these struts happen to be connected, we could just move this node in the same way that we've always moved him. Move this one here and then connect those up, and this will be a connected structure. But anyways, yeah, now we have both of those. There is some sort of fire alarm going on outside. I think it should be fairly faint on the recording, but hopefully you guys can't hear it. Okay, I just waited until it went off. I wasn't sure if you could hear it or not, and I didn't want to ruin the audio. Now that we've mirrored, there is one thing we need to do. If you'll remember correctly, we had this guy interfacing with the main strut, and is it smart enough to do that? I'd be actually very surprised. 61 and 63. No, it's not. Okay, I didn't think so. So essentially we want to go to Tools, check coincident nodes, and then where is the node for this guy? 61 and 63, 33 and 34. Oh, did we not actually move? I see. So what we're going to want to do is, I get confused because I remember we didn't move this strut. So I was like, why isn't there the node there? But it's here. There's just two of them. So we're going to go to check coincident nodes. We're going to select this guy, and 61 is the one that we want to keep alive. So we're going to set the tolerance to 1. So essentially anything that's within 1 inch of each other will be merged, which these are, I moved it half an inch, so they're less than 1. Action will be merge. Keep ID, we want the keep. Actually, we can do select. I know it's a higher ID because it's 61, I think. The other one was 30 something. But we can also do select nodes to keep, and then move to, I think current location is the one we want. Let's just make sure. Select nodes to keep. I want to select this one, and then OK. And yeah, it properly merged. So now we can see 61 and 63, 33 and 61. So now we're all merged up. Okay, so I think in my model for flare, I did add a foot pad. So might as well do that. It basically does nothing except kind of help you orient the model. It certainly isn't very important in the actual results of the beams. So let's just go to shape. We're gonna do a circular bar. And I think, let's just check our documentation here. Oops. I should probably turn off that Windows hide the taskbar thing, huh? Where is it? I thought I had documentation that said how. Oh, here it is, 36. Yeah, so we want a radius of 18. And then OK. And then it calculates all of our section properties. And then we can go ahead, let's put it on main struts. We can just go ahead and do model node. OK. And that was node 80 created. Modify, move by node. Select 80, remove 21. Move along vector. And then I think let's just move it 2 inches down. And we want that to be in the negative Z direction. Great. And then let's do a, is that straight down? Yeah, I think so. Model element. We will do foot pad. This guy and this guy. Okay. So the orientation, we can just select a node for it. Again, it's circular, so it doesn't really matter. The reason it threw an error is because we left it at CSys, so it went with the x-axis, but it threw an error because the element is already like orthogonal to one of the axes, or maybe it defaulted to the z-axis. That would make more sense because orientation essentially selects which direction the y direction of the beam will be. Okay, now if we do thickness, you can see it doesn't fill in the surface. So you can see like the tubes here look a bit more real because they have like two surfaces. But again, it's still not filled in. And this guy is just not filled in. That's just the way the program draws beams. But now we can kind of orient ourselves and look at that, guys. We got that looks like a lunar module landing leg, no? And then you'll see on this other model, I have a bunch of stuff for flare here, like tapered elements and stuff, but we'll do all that pretty quickly. This video is rapidly approaching 2 hours, which was not my intent. I think in the future I'll have to figure out how I want to do these videos, because I'm not sure who's going to want to watch 2 hours of this. So anyways, we're going to make a new constraint. We're going to call this constraint at LM. And now under that constraint, we're going to do nodal. And we're just going to select all of the nodes that we created for these spring elements. So actually, I think while I'm doing this, I got sidetracked and didn't tell you the other benefit of the spring element. For like all this type of stuff, they are extremely easy to output the forces in all 6 directions. So you can very easily analyze the forces on all your bolts with spring elements. So like essentially you just represent your joint like this, you get the force on the joint, and then you can take that like into a hand calculation spreadsheet to calculate your joint bolt failure, your lug joint failure, whatever. So that's another huge benefit, that they're very easy to get forces from. Let me make sure I got all of them. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. I think I got them all. And then we'll hit OK. And then we want to do fully fixed, because these are points that we want to be fully fixed. And then the spring controls the rotations. But again, if we wanted to, we could constrain like just the translations here and let and like make that our ball joints. But again, we can't do that for like all these intermittent joints like these guys, because if you constrain those to ground, like this is essentially constraining them like to ground, right? Okay, so now we have constraint on node, and this pops up and it shows you 1, 2, 3, 4, 5, 6 at all the different points. But we can turn that off by clicking this button. Okay, now let's do our loads. We'll do this real quick. We'll make 2 loads. We'll call it foot pad. I think we'll do one that's like a little bit slightly different than last time. 800, 800, and then 3000. So this will be 800 pounds in each direction horizontally along the ground, and then 3,000 pounds vertically. Like I said, I have no idea how much load the crushable that we talked about, the honeycomb crushable, will actually start to crush. So these are total assumptions. I could be completely missing the mark here. But again, we're just kind of going for analysis that's fun. Not necessarily to be like completely accurate to like what loads the lunar module actually experienced. So we're going to go to nodal, select nodes to apply a load to. So we're going to go on the foot pad, hit OK, and we're going to keep it on force, and we're going to change our X will be 800, Y will be 800, and Z will be 3000. And now we can see a load showed up 3,206. We're going to copy this guy, We'll make another one just because we'll do 0, 0, 10,000. Just so we get a little variety here. So this will just be a pure vertical, like they slammed it into the lunar surface. In reality, these numbers might be identical. Because again, like we're fully limited by the crushable and what force it starts to crush at. So this might not be physical, but we're gonna hit edit load, but you know, it just kind of gives us a, oops, we don't want any time frequency dependence. That's for transient, like time-based analyses, which is just a static structural. Okay, so that looks good. Looks good. Okay. And now we're just about ready to run. Sorry that this video is so long. Like I said, I'll maybe try to figure out a better way to do this. Title, we're going to do, let's say landing forces. Because, you know, there'll be other forces like launch forces and all that stuff. Next, launch forces will be in the stowed position, but still. Actually, I kind of jumped the gun here. So analysis program, you can select different solvers if you want. I always go with SimCenter NASTRAN. Analysis type static, normal mode / eigenvalue. That's if you want to find like the natural frequencies. There's transient dynamics / time history. That's if your load varies with time. Harmonic response spectrum, random response. Those are all like more vibration stuff. Buckling is, you know, if you want to find at what load the structure buckles. And there's a bunch of other stuff. Nonlinear static is for like material properties if you want to represent like yielding of the material and all that stuff. So we're just going to go with the simple one, which is static, and hit next. This stuff you generally don't need to change if you're just running a quick analysis. If you're running gap elements and solving gaps as contacts, you want to turn on the iterative solver. This stuff, sometimes there is some stuff in here that you want to set. So weight mass is one. If you're using body accelerations, you'll want to set that to the appropriate value for what units you used. Large angle and large displacement are often used if your structure deflects significantly enough such that like the stiffness of the structure changes drastically based on like the deflected shape. So essentially it recalculates the stiffness of the structure constantly to ensure that it's accurate. And then there's some other stuff in here, but we don't really need to worry about that. And then portion of model to right, this is the groups. We didn't talk about groups, maybe we will in the future, but essentially you can only, if you want, you can like omit elements or parts of your model. But we're not going to do that. These are geometry checks. We're going to leave these off for now. A lot of times it is good to set your weight and ground checks just to make sure your model's constrained and working properly, but we're not going to look at these files. Generally in more of a professional environment, that's something that you look at to make sure that your model is running properly. Master requests and conditions, we are not going to put any, so we actually want to change this to none. This is essentially, we can actually use a master constraint, but I generally don't like to use master constraints and just do it based on a case. These are your output requests. So displacement, load, and constraint force, we want those. Force and strain, we definitely want those. Total strain, elastic strain, I often find those are helpful as well, especially for composites. You want to look at strains. Thermal strain, don't really need. Strain energy is good if you're trying to understand like your modal and like natural frequency, and you can see where like a lot of your energy is going, so you can understand where to stiffen the part. Yeah, I think this is all good. Otherwise we don't have context, so we don't really have to worry about that. Hit OK. So now we have our analysis set, and then no cases defined. We're going to hit multi-set, and now we have our constraint at LM and our two loads, and just hit OK. And now that's created two cases, constraint LLM, footpad, and then the two footpad cases. So if we had like, there are some models that I've used that have like multiple constraint setups and multiple loads, and you can essentially do like every combination of constraints and loads if you want quite easily. Okay, now I think we're ready to run here. And I just realized that we never saved this, which is always good. Video one filming, sure, why not? So thank God nothing crashed because we would have had to restart. And let's go ahead and run this guy. It might fail. You know, I would say more than 50% of analyses fail when you first run them because you're just missing something, especially when you start using groups. If any of your elements, properties, whatever nodes aren't in the group, it'll like automatically error out. So I think we'll be okay though, fingers crossed. It'll be extremely quick. We only have, yep, it's done. Okay, so it didn't fail. And you can see here, this is like our solver messages. Let me make this guy much bigger. So you can see it took, this is the time, it took less than a second. And that's because there's 78 elements. When you get up to like, 100,000 elements, it can take, like, it all depends on the speed of your computer as well, like your specs of your computer, but it can take 10 to 20 seconds. Once you get up to like millions of elements, it can take minutes. Once you start iterating for either materials or contacts or displacements, it can take hours. So just keep all that in mind. And again, it'll depend. Like if you're using like an old laptop, it might take quite a bit longer. So anyways, you can see finite element model generation started, generated 474 degrees of freedom, loads and boundary conditions started, application of loads and boundary conditions successful, solution of equations started, successfully completed, and linear static analysis completed. And then this is essentially all the equations it's solving. So it solved 414 equations. Once you have a bigger model, you'll see that this is like generally in the hundreds of thousands or millions of equations that it solved. So anyways, there's the log. Oops, I didn't mean to do that. Or I think it just defaulted to that. Anyways, let's see if we got working results here. So first of all, let's start with our displacements. So total translation, and then we're gonna no contours. You can change this to contour, or you can hit this button right here. And let's see. This guy, it's 12. That's significantly more than the other model, but that's because I haven't updated any of these tubes yet. So this is actually going to have some pretty considerable deflections here. And you'll notice the default 0 color is magenta, which I think is terrible, because like you want like your nice like blue, green, red, and like that's super clear. Like red is bad and blue is good. But like what is this like pink color? I feel like it doesn't really fit in like the kind of like your generally good under like what's the word I'm looking for? It doesn't like, it's not intuitive, I guess. And I think they know this, but for some reason they don't set it to default, because there's literally an option here that says like I went to contour palette, and then there's literally no magenta, and you just hit OK, and then it eliminates all the magenta. So I don't know why they don't make no magenta the default. Maybe they're just stubborn about it. But anyways, if we go to deform, we can change the model to deformed, and then these are like very spindly tiny beams, so you can see there's a ton of deformation here. Like this would be an instance where like large deformations probably applies, right? Because this is significantly different stiffness than this. But you'll see once we thicken up these tubes, it'll pretty much be fine. And actually this is percent of model. Let's do actual. So a little bit better. And then we can change it to like, give us like the animation there. And then real quick, I just want to show this super fast. We'll look at it more at the end, but you can also output beam and a max combined stress. So this is the stresses in the beams, and you can see if we're doing like aluminum, 40,000 might be like a good kind of value to acclimate ourselves at. So we're gonna go max threshold, set this to 30,000, and you can see, yeah, as expected, all these beams here are generally not doing too great, because they're getting bent so much by a 10,000 pound force acting not along its center line. So let's go ahead and thicken up these tubes. So let's start with the primary strut. We're gonna copy this guy, and I think I just ended up on 7.0 inches. I think I just decided on, not for any like real reason. I just messed around a bit. So we're gonna go to shape, change shape, and we're gonna change the radius to 3.5. Hit OK. And now we're gonna go to modify, update elements property ID. Select all of these elements, hit OK, and we're going to change it to AL tube 7.0 by 0.08. And now that looks much better. And then I think I made it purple. I like to change my elements to different colors. Not as important when you're using beams, because like the did I make it purple? No, I made it green. Well, we'll just leave it purple. I was saying it's not as important to change element colors when you're using beams, but I find a lot of times with plate elements or solid elements or different materials, it's helpful to visualize where all your different materials and thicknesses are. Okay, so I think, let me just pop over to the other model so I can see what I did. Yeah, so I set these guys to rectangular tubes. Yeah, 2x2, just because I thought that more accurately represented this guy. Again, like I said, though, this would be a much more detailed model, but if we want to like try to start approximating stiffness for this guy, we can just do a new AL rectangular, and then 2x2. We're going to go to shape. We'll call this a rectangular bar, 2 inches by 2 inches. Hit OK. And now we're going to go to modify, update elements property ID, and we want this guy, this guy, this guy, and this guy, and then also the ones on the other side. This guy, this guy, this guy, and this guy. And then we want to change it to rectangular. And now we have that set up. What else did I update here? I think I made these guys. Let's see here. These guys I made 5 inches, the secondary struts. So let's make a, let's do a copy here, and then we'll do 5.0, and then we'll go edit, shape, change shape, and we'll take this to 2.5. Okay, modify, update elements property ID. So hopefully, you're starting to see, the sort of power here of FEMAP, that you can just like change whatever you want when you want. And especially it's good for like, you can just make all your beams. You don't need to know what shape they want to be, and then like define the shape as you do your analysis. Now I also will say, I'm doing this again for fun. There are many ways to analyze things. Not all analysis has to be finite element analysis, right? This structure, even today in 2022, might be easier and better and faster to analyze, like with hand calculations, using like an Excel notebook to calculate all of your strut vectors and your forces on it. So, a finite element model might not be the answer that you want for like getting all of your strut forces. Or maybe you decide that you want to do like an integrated model or something. So again, as an analyst, you should be like constantly questioning what's like the best and fastest way to get to the solution that you wanted. So let's go ahead and make these the tapered beams. So I'm going to copy this property, and we're going to call it AL tube, and I don't want to input, we're going to call it top outrigger tapered, just so I don't have to name it something. And then we're going to go to shape. Actually, cancel this for a second. We're going to go tapered beam. And then shape, radius of one end is good on that. And then we can go shape NB, change shape. And I think we'll do like 0.5 maybe. I think that'll be good enough. I mean, you can change it to whatever, but now I'm going to go modify, update elements property ID, and then we want to change it to the tapered one. And then if it doesn't change, Control G regenerates, and you can see it's backwards. So what I would do for this guy is do modify. Actually, let's just change on, turn this guy on, edit, and we're gonna just swap 2 and 3. And then again swap 2 and 1. So now we have like our nice tapered beam here. There are a bunch of other tapers that I did. So like this guy's tapered. This guy's tapered. So we need to add 3 more tapers. So like pretty much all 3 of these beams need a taper. So let's copy these. AL tube taper. And just call all of these tapers. And then I don't know if anyone's actually still watching or if anyone's going to watch this in the first place, but we are almost done. Just want to do these last few tapers so I can like legitimately accomplish what we set out to accomplish, which was recreating the analysis model at the beginning. And then if you guys are following along at home, you can keep running with this and pretty much do whatever you want. And maybe we'll revisit it at some point. So anyways, our 3.0 taper, oops, we don't want new. We want edit, tapered beam, shape NB, and change shape. And we can also do 0.5. Actually, I just realized we totally could use the same properties for these two, but oh well. I've already gotten this far. Shape NB, this is the 7.01, so let's bring this down to like maybe like 1.5. again, this is geometry you would have at your fingertips, like exact geometry when you're in industry. But for now, I'm just, kind of making some assumptions here. And then shape NB, this is the 2.51. So let's just go down to like 1. Okay. And now let's do modify, update elements, property ID, this guy and this guy. And then we'll do, there we go. This one is going the right way. The other one's not. Let's do edit and do 26 and 25. Great. Modify, update elements, property ID. I think, yeah, all these, let's just make them tapered. As well as this guy and this guy. Yeah, and the ends of these guys. I think that should be all of our tapers, at least the ones that I selected before. And we just want to make this 3.0 taper. Okay, and again, some of them are right, some of them are wrong. So these guys just need to have their nodes reverse 52 and 24. Control G to regenerate. 78 and 79. Control G. 47 and 46. Great. Are there any that are backwards? I think we got them all. Okay. So yeah, I think that's that analysis model pretty much recreated. This is what I started with. So let me just hit the analyze button. FEMAP seems to think that I'm out of memory. I thought that was an error, that we messed something up. I don't know why it thinks that. I have like 32 gigabytes of memory, and it seemed to think that I only had 3 gigabytes left. So it might have done like a huge spike or something for like a millisecond. But actually, does it say it over here? Physical memory, 32 gigabytes. Oh, you can see my you can see my specs. AMD Ryzen 3700X 8-core processor. Anyways, that worked. It just for some reason thought I was out of memory, which is definitely not true. So we're going to go to the same analysis, and we will turn on total translation. And now you can see, I have it at 30,000 still, automatic. And now you can see it's like a much more reasonable value for our deflection. And then we can mess around with the animation as well. If I go to like 16 frames with like a 50 delay, then it'll be like a pretty smooth animation here. Even more frames. You can see there are deflections. And then if you want to see deflections in like most of the deflections are limited here, but like, struts do move a little bit as they are deflected under load, and you can see that quite a bit more when you like ramp up the deflections to like 10x, and now you can see like the rest, like you can see the outriggers swing as you kind of expect, and then like the deployment mechanism is here again. Remember, this is 10x deflection, so it's like almost imperceptible. Like you can barely see it moving at when 10,000 pounds is applied, and the struts are compressed and stretched. But like at even 20x, you can see much more of that like compression and stretching as struts pick up load. Let's just set this to that. We'll set this to 5 for visualization purposes. So that's total translation. Let's go back to contour. One thing that I always find very valuable to look at, especially for minimally constrained assemblies, which again, a lot of times you can do in Excel, but sometimes you want them as part of your model so you can get all of your constraints right. If you go to like axial force, you can look at, so we have our legend here actually, and I'm going to go hit F6 here, and we'll go to post-processing, legend, and then label. We're going to go view color because these set to like, yellow. How are you supposed to see that? But anyways, you can see now here we're looking at axial force on the beams. And this goes from negative 12,000 up to 6,000. And we can kind of look at, based on what color the beams are, if like our analysis passes, sort of like a sniff test, I guess. Right. So let's start with our primary strut here. The primary strut is in compression, which is spot on, right? So that is right. Let's just turn off deflections here. I think it might be easier to look at. Primary strut is in compression as this force goes through this point. Makes total sense. These secondary struts here are in tension, and that makes sense because we have this point right here. The load is acting through this point, and we're essentially trying to twist this entire strut up, and then these secondary struts are in tension as they attempt to constrain the primary strut from rotating around the outrigger. So that makes sense that it's in tension. Again, jumping in here a bit more, the whatchamacallits, the cross members are in compression. You can see they're blue, which is negative 5,000. That makes sense, right? Because if these guys are in tension as they try to constrain this from getting pulled around, that means that the triangular assembly here is getting pulled inward. And so like this inward force is being reacted out by the cross beam here. And then this guy is in tension. Again, that makes sense because this guy is in tension, right? So that it makes sense that they're both in tension, and this is in compression to keep that from collapsing in on itself. So hopefully that all makes sense. And then outrigger here, right, it's being pushed up. So the bottom struts are in tension and the top struts are in compression, which totally checks out. And then it looks like the triangular bit right here isn't being loaded a ton because like this force is acting in plane with this force. So that all looks like it pretty much checks out. So, always good idea to look at your axial forces to make sure that they all make sense. And now we can also look at our combined stresses. So let's set this again to max threshold, and we'll do 30,000. Maybe we'll do like 20,000. Yeah, that's probably better. So now we can see we're looking at max stress. We can also look at min stress. So you can see like the obviously our primary strut has the most stress because it's being bent. So combined stress includes the forces of axial and bending. So like it calculates the bending stress exactly. Like it's not like like it uses the actual equations and not like a approximation. It looks like we have quite a bit of stress on the fork here. Wonder how much that is. It's not a ton actually. You can see it's like 22-ish thousand, 20,000, somewhere around there. So it's not a ton. But we can also check NB. So like essentially it recovers stress at the endpoint of the two elements. They're generally fairly similar in A and NB, max combined stress, but sometimes they're different, especially if you have like one element that's representing a cantilever beam, right? And A and NB are going to be extremely different stresses. So it is important to check both of those. Worth noting, beams do not do what's it called? Torsional stresses, because torsional stresses in like anything except circular tubes are generally very messy solutions. So like I said, beams calculate exact stresses using like the theoretical equations. So torsion, generally doesn't have those. And then the last thing that I will show you guys is if we go list output results to data table, and then just hit OK here, and then select our analyses. And like I was talking about with the springs, you can output the Bush X, Y, and Z forces, and we'll just do it on the outrigger real quick here. And where's our data table? It's right here. So now this is output all of the forces on the different spring damper elements. So you can see ID here. That's the element ID 43, 44, 45, 46 for identifying it. And then these are all the forces. So you can see X, Y, Z for each of the analyses that we ran. And it outputs like the exact force in each direction. So you can, use that in other analyses to evaluate bolt failure. So anyways, guys, that's it. Make sure I'm still recording. Wouldn't that be terrible? I just finished the video and realized I wasn't recording. I am. So that's all I got, guys. This is the first video on the channel. I plan to do, a decent amount. I've always enjoyed like the kind of teaching engineering aspect in the times that I've done it. So I thought maybe there's some people out there that would be interested in hearing, all this type of stuff. I'm going to do a few different types of videos. I think I'll probably do some videos like this where I just sit down and make an analysis model like live and on the fly with you guys. Or I guess it wasn't super on the fly because I prepared beforehand, but still. But I think like my next video, I'm going to do more like maybe like a 10-15 minute chat about like a particular topic, which is more like bite-sized, and you don't need to really like watch every single click that I'm doing. And then maybe just some like where I create an analysis model and go over it instead of creating it live. But I'm interested. Did anyone get this far? Did you watch the whole video? What did you think? Any requests? I'm going to be doing tons of different analyses and like topics from both like spacecraft and aircraft. So hopefully it should be fun, and hopefully some of you out there are at least a little bit interested. So let me know, did you get this far, and let me know what your thoughts were. But anyways, guys, yeah, I'm not sure what my posting schedule will be yet, but I'll see you next time, hopefully in not too long of a time. So thanks everyone for watching. Bye.